All right, so welcome back. Today we actually covered the last day of new material, so that's kind of exciting. And in terms of um, difficulty level, it's going to incorporate a lot of things we've already seen and kind of be a good comprehensive review, not only of the things that are important in this unit, but also kind of looking back some of the skills we learned earlier in the course. So what are we covering? We're in section 5.5. And we are going to pick out a small selection of 5.5. We're going to focus on what's called the double angle formulas. And we're going to focus kind of like we did in 5.4 on sine and cosine, and then just kind of take a brief look at tangent. My little one is getting ready to wave. I think I promised him a wave. Okay. Okay. Go have a seat. All right, mister. Go have a seat. All right. So if we remember from last time, we were studying the sum and difference formulas. So we had these formulas that told us what to do if we were looking at the sine of u plus v. Oh, and we have someone else joining us. So we'll pause just a second. Let them get in and the audio get turned on. I'll go ahead and finish writing this formula here. So we had sine u cosine v plus cosine u sine v. Right, I think we're still waiting for audio on our new person. But what we want to do in this case is think about what happens if instead of just two different angles, u and v, what if we have two angles that are actually the same? In other words, what we're going for, this idea of a double angle, is talking about if I know the sine of u and the cosine and the tangent, because if I know one, I can get the other 6 trig functions. So if I know sine, I can get cosine and tangent. But if I know sine of u, can I find sine of 2u, the double angle? And so this 2u is the double angle part of it. And if we plug in and we think about what happens if this becomes a u and then also a u here, this actually turns into sine u cosine u plus cosine u sine u. Now, in terms of these two, notice that the order of multiplication doesn't really matter. So we could just flip those around and that would be fine. So if we flip that around, notice that what we really have is sine u cosine u plus sine u cosine u again. So at this point, we have two identical things that match up. We have two like terms. So we really have 2 sine u cosine u. And I think these u's drive me nuts a little bit. I like to write mine with x's, but sometimes it's kind of nice to put our parentheses just to make sure we have those parts and we're not just making a run-on of trig. So this actually gives us our first double angle formula. We're just taking that sum and difference formula, putting in the u plus u, and it gives us our first double formula or double angle identity. So the sine of 2u is 2 sine u cosine u. Now, in terms of going forward in the class, or I should say other math classes, this is the one that I found that I use the most frequently. In other words, this one, the double angle for sine, is one that we see not like all the time in calculus, but you see frequently enough that it's a good one to know. Now, in terms of the cosine, we're going to apply the same sort of thinking. If we recall the sum formula for cosine of u plus v, we're going to substitute that v for a u and see what works out. This one, I would say I run into less frequently, and then the tangent kind of gets further and further down on the list. So let's go ahead and take a look at our cosine of u plus v. So if we're taking a look at our formulas, this one starts off cosine u, cosine v. We have an alternate sign, and then we have our sine u and sine v. So in this case, if we are thinking about plugging in and substituting notice what we're going to get out. Cosine of u times cosine of u. We could write that as cosine squared u. And then sine u times sine u gives me sine squared of u. Sorry, guys. Turn the sound off.
Oh no, that was my
Hold on, sorry, guys. It's just a second. Sorry, guys, had to take care of one quick thing there. So if we take a look at condensing this into our formula, sorry, y'all, that's family on FaceTime. Cosine of 2u, with my little one, gives us cosine squared u minus sine squared u. Now, this one sometimes I think can be a little bit trickier. Let's see, I don't think that I'm not on mute anymore. Make sure to double check that. This one I think is a little bit trickier because it kind of looks like the Pythagorean theorem identity, but it's not quite. But the nice thing about it is because it reminds us of that, we can actually make some substitutions and rewrite this one two more different ways. So I like to think about this one kind of as the core double angle for cosine. And then if I need to transform it, I would. So remember your Pythagorean theorem identity. Sine squared, we'll use u's since we're using u's here, plus cosine squared u equals 1. So this tells me if I wanted to rewrite my cosine double angle and just write it in terms of sine, I could say cosine squared u is the same as 1 minus sine squared u. I could replace this chunk with all of that. So let's do that. We've got that. Keep in mind, we're going to put in that 1 minus sine squared, dropped my u there. So that was the piece that I was substituting in for my cosine squared. And then I had another minus sine squared u. So in this case, we've got 1 minus 2 sine squared u. And then if we wanted to rewrite it another way, we're going to go back to our identity. So the cosine squared, cosine 2u equals cosine squared u minus sine squared u. And this time, let's think about the reverse. If we wanted to swap out our sine squared, we know that sine squared u plus cosine squared u is 1, then sine squared u is 1 minus cosine squared. Okay, so let's drop that in. And then on this one, we'll just be careful, distribute our negatives and clean it up. So 2 cosine squared u minus 1. So this actually gives us, if we bring it down, our third one. So I'm just going to rewrite cosine 2u. And if we kind of highlight the 3 for our cosine double angle, I would jot all of them down so that you have them handy. Because you're going to see in the WebAssign homework, and then we're going to explore a little bit more in the Desmos, you're going to get a chance to work with all 3. And again, I wouldn't necessarily recommend committing all 3 in memory. I would just focus on being able to use them when you see them. Just a quick aside about our test 4, we'll talk more about it at the end, but you are going to be allowed, kind of like last time, just to have a note card, really just to condense your ideas, write down all these formulas. So I would put all 3 on there. So let's go ahead and I'll pause for a second. Any questions so far? You can drop in the chat comments if you do, or unmute yourself. Okay, it looks like we're good to go on. I'm going to stop this share And I'm going to go ahead and share my Blackboard page. Because what we have here, I went ahead and clicked into our course content, our Unit 4 and our section 5.5. And this is kind of the screenshot from your textbook for your double angle formulas. So notice we have sine 2u, cosine of 2u, with the 3 different versions for cosine of 2u. And then we have the tangent of 2u. Now, I'm not going to spend too much time talking about the tangent, but the idea is the same. If you go back to the tangent of u plus v, substitute u in for v, you get the double angle here. I believe on your WebAssign, don't want to tell you wrong, but I believe they're exclusively sine and cosine, that you're not going to see that tangent. And definitely on the test, you will have double angle for sine and cosine, but I probably won't put any tangent on there unless it were something like a bonus. So let's go ahead and see the types of problems we're going to do with these. I'm just going to switch us over, like get us to the right place, to, there we go. Some of the stuff on the WebAssign. So it's very similar to the beginning at 5.4. You're going to start off just by completing the identities that we just talked about, and then kind of selecting all on this one. Then the types that we're going to see are going to be things like solving equations, rewriting an expression, kind of making it a new identity, and then we're also going to go back to the idea of, if I give you a value for a trig function, find the other ones. It's very similar in thinking to using our Pythagorean identities like we did before, incorporating the quadrant, but then we're going to layer in double angles. Okay, and then we've got some graphs. So what I'm going to do is swap us over, and we're going to look at similar problems of all of these so that you kind of get a feel for what we're going to be doing. But as far as new content and what the section deals with, that's it. Those are the 2 main things that you're going to have. Double angle sine, double angle cosine. All right, so let me see if I can make sure all this is up and going. Okay, sorry, it takes me a second, guys. So let's actually start with an equation in this case. I think this one may be the identical one that you guys see in your WebAssign. That's okay. You're going to see more identities or expressions than equations here. I'll kind of try to see why as we go through this example. But for this example, they tell you to solve the equation. Cosine 2x plus sine of x equals 0. So if we think about section 5.3 on solving trig equations, our core principles were to isolate the trig function and try to just get one trig function. So it was really hard to work with both sine and cosine or multiple trig functions. So if we can think about a way to convert one of these two to the other trig function, that's going to serve us well. Now, when I look at this one, since we are in the double angle section, I'm seeing that cosine of 2x. If I remember, hey, that's a double angle, there's identities, I'm going to look back at the ones we just did and see which one is going to serve me. If I am trying to convert back, I guess this is kind of the, this is a quick note, this is kind of the original one here. I'm going to try to convert everything to sine since I already had a sine in there. In other words, if I convert that cosine of 2x to a cosine squared minus sine squared, I'm still going to have that cosine squared, and I'm going to have to keep on working on it. But if I go ahead and choose to use this first one, 1 minus 2 sine squared u, that's going to convert entirely to sine, and it looks like it's going to give me a quadratic equation in sine of x. So let's do that. Okay, so we're going to have 1 minus 2 sine squared, and instead of u, we've got an x. So just be careful. One of the things I do most frequently when I'm looking at these, sometimes I accidentally put, instead of the x here, I put a 2x or just some sort of typo there. So let's clean it up. And since I see this squared, I'm going to think about writing it with my sine squared term first. And I'm just going to drop my parentheses. We don't really need that. And I am going to think about putting that +1 at the end. So, questions so far on this part? So let's think about approaches here. At this point, what we want to recognize is this is very similar to the idea of negative y squared plus y plus 1 equals 0. It's a quadratic equation, just substituting y equals sine of x here. So if we see that, I would probably do a little bit of cleanup. In other words, I don't want to try to factor that negative. We could, and I would love to avoid quadratic formula if I could. So let's go ahead and I'm going to multiply both sides by -1. I'm just going to keep that 0. And then 2y squared minus y minus 1. Or you could think about it like adding the 2y, subtracting the y, subtracting the 1. And take a minute, and I want you guys to write that guy down and see if we can factor. I'll fill in some ideas here. So hopefully you realize that if it factors, we should get a +1 minus 1. Make sure that's in the right place. So that gives me the -1 at the end that I need. And then -2y plus y gives me my -1y. So if I kind of go back to my trig in this case, this is telling me that transforming this, you could still multiply by the -1 and the -1. Maybe I should do that to make it a little bit more clear as an intermediate step. And then go ahead for your factorization. So 2 sine x plus 1 and sine of x minus 1. So at this point, now we have 2 pieces to deal with. Let's go ahead and copy them over. Make sure we get those right. And we want to think about setting each one to 0. Keep in mind, both of these separate equations could have one solution, multiple solutions. And if we're looking at the directions, they're going to tell us in some of the ones, find all the solutions in this particular example between 0 and 2 pi. But then you could also extend this to find the general solutions by looking at adding that plus 2 pi in and doing that. So let's start with the one on the right. I add the one sine of x equals 1. So remember unit circle, keep going back to that. We're going to think that's where our y value is 1, and that's going to be at pi over 2. I think it did put our answers in radians or assumed to put them in radians. Okay, so pi over 2. And then if we keep going, then this gives me 2 sine of x equals -1, sine of x equals -1/2. And then when I'm thinking about this one, that's going to put me between, or it's going to put me either in quadrants 3 or 4 in this case. So if we think about this guy and think about my angles, it's a pi over 6 reference angle. And we could think about, my brain thinks about that guy as negative pi over 6. But it's going to be more helpful to go ahead and convert it to between 0 and 2 pi. So let's go ahead and think, well, if that's really 2 pi minus pi over 6, or 12 pi over 6 minus pi over 6, we've got 11 pi over 6. And then I have in my third quadrant pi plus pi over 6. which gives me 7 pi over 6. Now, this should be all of our angles between 0 and 2 pi. And just like we did on Monday, we want to make sure we follow this up with a check in Desmos. So let me swap over and do that. I think, oh, not that yet. Let's see. I'm just going to open up a blank Desmos here. And let's go back to the original equation. I'm going to put in cosine of 2x plus sine of x equals 1. So I'm only looking at 0 to 2 pi. Let's go ahead and restrict our domain here. Sorry, guys, I'm fighting our pictures. They keep covering everything up that I need to see. Let's do steps to pi over 6. So notice I'm seeing my pi over 6. There's my solution. I'm seeing 7. Uh-oh, what did we do? So I'm seeing my pi over, no, I'm not seeing my correct solutions. So let's go back and troubleshoot. So first of all, let's make sure I entered everything into Desmos correctly. Oh, I see the problem, you guys. You guys probably would spot it if we were all in class together, because I look at this and I say, oh yeah, these don't match up, right? Which means either, number one, we solved the equation wrong, always a possibility, or number two, which happened in this case, I typed something in Desmos wrong. So look at this part, guys, equals 0. If you look back at your original equation, or it says equals 1 here, it should have been an equals 0. So just double check before you declare that you're wrong, because now this is at least looking a little bit better. So let's take a look back at our solutions and see if this matches up with what we were expecting. So notice on this is a little bit better. Notice I see my 7 pi over 6 and I see my 11 pi over 6, but I'm not seeing that pi over 2. Okay, so maybe we need to investigate a little bit further. So remember, if things aren't matching up, we had that problem with the one example last time where we were missing a solution when we did it in this view, and then we actually saw the intersection better when we graphed one side of the equation and then the other. So again, some Desmos limitations. Let's investigate whether that's the case. So said this also has some advantages of giving us some insight into the shape of the graph. When we zoomed out, we saw that our graphs were out of phase. So we still see a periodic graph, but not our traditional sine and cosine graph. You know, let's just zoom out for a second. So you can kind of see between 0 and 2 pi. Then we're going to start repeating again. Okay, there's between 0 and 2 pi back. So in this particular case, this is our left-hand side. And then our right-hand side, we want to do y equals 0. Now, in terms of my intersection, notice I do have a pi over 2, 7 pi over 6, and 11 pi over 6. Meaning, again, guys, I'm not sure why Desmos has a harder time when we're graphing the complete equation equals 0, but this is just something that we need to be aware of. We're not spotting the solution there. Now, in order to check whether it's a solution and not an extraneous solution, like if this is occurring, I always ask myself, can I plug pi over 2 back in to the original equation? In this case, if I plug pi over 2 back in, I'm looking at cosine of pi, which is -1, plus sine of pi over 2, which is 1. Both of those have no domain issues, so -1 plus 1 does give me 0. To check, it should be a solution. So again, maybe I can troubleshoot Desmos a little bit and figure out what's going on there, but that's kind of the Desmos issue. So questions on this one? So moral of the story, do by hand, check both ways on Desmos. And a lot of your equations in this particular section have this sort of feel. Once we eliminate or use our double angle formulas to eliminate either sine or cosine, kind of reverts back to a 5.3. So let's go ahead and I'm going to share my screen again, and let's pick another one to take a look at. So if we take a look at just using the double angle formulas to rewrite the expression, let me give you a couple examples of this. So again, just jot something like rewrite the expression, meaning we should have an equivalent expression. We'll talk about how to check these, but let's say we have something like sine or 16 sine x cosine x. Well, right now, we don't want to think about like necessarily the goal is to eliminate one of our trig functions, but that's what happens a lot of times when you're using your identity. So when I see this, my brain is saying, hey, when you have sine of x times cosine of x, that product is related to your double angle. So what we know is that 2 sine x cosine x is the same as sine of 2x. And so what happens is our expression is really 18, 8 times 2 to give me 16, 8 times 2 sine of x cosine x. And so this guy gets replaced with sine of 2x. So our total expression is 8 sine of 2x. Notice that coefficient just gets cut in half, and then we introduced our double angle. So you have some variations of this. If you think about what would happen, excuse me guys. Oh, hold on a second. I have a tissue. Sorry guys, tissue box across the room there. But if we had same thing, go to 15. Think about your process is really the same. What you're thinking here, it's maybe harder to kind of do that multiply by 2 idea. But if we wanted to write this as 2 sine x cosine x, in order to make this balance out, we can't just say it's 2, right? We can't just change the 15 to 2. But what we can do is multiply by 2 and divide by 2. So this becomes 15 over 2 times 2 sine x cosine x. So if you think about canceling those 2's, those cancel back and you get an equivalent expression. So notice what happens. This guy becomes sine of 2x, and then you have 15 over 2. So you're still cutting that coefficient in half and then introducing your double angle. So questions here on these 2 examples. Okay, so let's take a look at one of our other ones. I'm going to pick one. In this case, it looks a little different. So same directions, we're going to rewrite the expression 6 cosine squared x minus 3. And in this particular case, we have a cosine squared. And anytime you have that cosine squared, my brain is thinking, well, not only trig, trig Pythagorean theorem, sine squared plus cosine squared equals 1, but I can also think about my double angles. And in this case, again, it gets a little bit trickier because you have to think about which double angle you want. Let's have a little more room here. So the core one, I can write it today. The core one that we want to know is the cosine squared u minus sine squared u. But then the other ones that we want to do, we can just kind of look back if we need to. Substitute those back in. And let's go ahead and write them out. So we have 2 cosine squared u minus 1. And 1 minus 2 sine squared u. Because when I see this now and I have them in front of me, I could do some manipulation with this guy. Okay? But the most obvious one to go for is your second cosine double angle. Because if we pull out our common factor out that 3, now I have something that matches that. Okay, so always factoring anything you can is helpful. And then don't forget about all of your different forms. And replace all of this with cosine 2u, or x's in this case. Now, let's talk for a minute about checking these because we didn't check our other two. I'm going to switch us back over. Let's see, to Desmos. Turn these graphs off here. Maybe zoom out a little bit. Turn off that y equals 0. And let's graph our original expression. So if I graph 6 cosine squared of x minus 3, and then if I graph 3 cosine of 2x, oops, I'll get parentheses. Nope, still didn't get those parentheses. Struggling with the parentheses here. 3 cosine 2x. Notice they match up. Now you've got the purple, our original, and then our simplified expression. So you can check whether you're simplifying correctly, kind of like we checked those identities. As we do each step in our identity, it should match up graphically with the line before. So questions here. All right, so the last type that we actually have to look at is given an actual trig value, finding the other trig values. So let's quickly take a look at one of those. Let me switch us back here. And there's 2 types. One where they give us a picture. I actually think the picture ones are a little bit easier. Those ones are like 10, 11, and 12 on your WebAssign. Start with that one. So in this particular example, we've got a triangle, and they tell us where theta is. And then in this one, they have 1 and 6. They do mark the right triangle. And what they ask us is, based on this picture, find sine of 2 theta. Now they could write it either just like I've written here, or you could put your parentheses around your 2 theta, same thing. You want to assume that when you don't see a parentheses like this, that's the entire argument. Whereas, in other words, that's the same thing as sine of 2 theta. The parentheses can be understood. If you're not sure, add them in. So let's think about what I would do in this case. When I see my picture, we know right triangle trig tells me sine, but it's sine of theta, not 2 theta. Sine of theta is going to be opposite over hypotenuse. But now I don't know that hypotenuse, right? So I need to think, oh, that's my C. So C squared equals 6 squared plus 1 squared. So if I add my squares together, I've got 36 and 1, which gives me 37. I've got the square root of 37 is that hypotenuse. Now, you can go ahead and clean these up and write square root of 37 over 37 by rationalizing the denominator, or you can kind of like let it ride and clean it all up at the end. Now, are we done? No, right? We know sine, but we really want to know the double angle. But when we remember the double angle formula tells me if I know the sine of the original angle, which now I do, and I know the cosine of the original angle, which I could kind of go back and think about from the picture again. The cosine is going to be my adjacent over my hypotenuse, square 7. So 6 square root of 37 over 37. Then I can drop those into the formula and do 2 times their product will give me the double angle. So it's essentially asking you, hey, can you still use these triangles to find your sine and cosine? And then can you drop them into your double angle? So again, kind of a good review of the things we have done before. So let's go ahead and clean this guy up. So 2 square root of 37 over 37. You see why? I'll illustrate this one way and then illustrate the other way. Y'all, this is messy, right? I don't want to look at this, right? Because I have all these radicals and now I have 37 times 37 in the denominator. This really is going to illustrate why cleaning it up and plugging in is not always the best thing to do. If they had just asked me for sine and cosine on WebAssign, they would have wanted the cleaned up versions. But in this case, back up a second and notice what happens if you plug in the unsimplified version. Life is easier. Because what we're going to see, 1 over square root of 37 times 6 over square root of 37. Oops. So guys, writing on the arrow button here. Skip this over. Okay, so this is going to give me, think about this as 2 over 1. So I've got 12 if I multiply my numerators. Square root of 37 times square root of 37 gives me 37. Much, much better, right? Okay, so don't clean up to the end. Sometimes is the moral of our story. Now, in this particular one, they only ask us for sine of 2 theta, but they could have asked us for the cosine double angle and the tangent double angle if they really wanted to here. So questions on this one. Okay, so here's what we're gonna do. We're gonna stop and take our break, and when we come back, we're gonna do the other type where they don't give us a picture, but they tell us information about what quadrant we're in and ask us to find the other remaining trig values. And then I'm also gonna, when we come back from break, talk about our one Desmos activity, our last Desmos activity that you guys will be set up to handle. So it is 10:40. Let's come back at 10:50. If we have any questions on this one, I'll give you guys a couple minutes to look at it and ask, and then we will pick up from there. Any questions before I stop our share and close this for now? Okay, so I will open us back up a minute or two before 10:50 and see you guys then.